Hi, I'm Shinya Narita, at University, Japan. I'm very happy to be a lecturer of this short course. And today I'm talking about the overview of gas phase experiments. So here are the contents of my presentation. Some topics are the introduction followed by the recent significant studies, hot gas experiments, and then the summary. So starting with the introduction. At first, characteristics of the gas phase experiments. Among the various experimental methods in low-energy nuclear reaction research, gas phase experiments have the following characteristics. Well, this might be somewhat a personal view, but anyway, the experimental apparatus can be designed with a good flexibility, and the temperature of the sample can be accurately measured by various methods, such as the contact and non-contact type devices. And this is an advantage in precise evaluation to excess heat. And it's suitable for the radiation measurement, especially in the low pressure environments. And that gives us direct evidence for occurring nuclear reaction. And contamination of the impurities can be minimized by using high purity gas. This is an advantage in searching for transmutation products. And from the aspect of the developing practical technologies, such as the energy source, it is preferred to use gases that are convenient for the transportation and storage. So in fact, the gas phase experiments have been conducted since the early days of the low energy nuclear reactor research. I'm showing the brief overview of some of the representative ones. One is deuterium gas loading and unloading experiment with the multi-layered metal sample. This is done by the Yamaguchi. I don't know say so much details here. So in this experiment, the surface coated palladium sample was used. In the experiment, the excess power generation was observed with almost 100% reproducibility, and the peak excess power was estimated as much as 8 watts, with the input being the 0.1 watt. And the phenomenon was found in both hydrogen and deuterium experiments. And the other study is the deuterium gas loading with fine particle using double structure reactor. This is called the DS reactor. This experiment is done by the Arata. The reactor, this is the reactor cell, the view of the reactor itself. Then the reactor is composed of the inner and outer cells, and the sample was put into the inner cell, and hydrogen or deuterium gas was supplied from the outer cells. And so in the experiment, these samples, palladium black and nano-palladium, were tested with the hydrogen or deuterium, and they observed numerously large heat evolution using the finer particle palladium. I mean, that is nano-palladium with deuterium gas. So these new findings have been accumulated through the progress of some studies. So here what we have learned from the gas phase study so far, and critical conditions in the gas phase experiment. I mean, the loading and unloading information are becoming clear through some experiments. So as for the sample conditions, so that is sample being the host material, and at first non-size, fine structured metal is some important conditions. In addition, metal composite, or the metal and metal oxide composite seems to be a key in the condition of the sample. So for the reactant, both hydrogen and deuterium are possible. And for the gas temperature, the higher temperature gas seems to be the better. So in the experiment with the combination of these conditions, anomalous heat evolution, well, excess heat have been observed with higher efficiency. Especially in recent years, important results have been obtained in deuterium or hydrogen absorption-desorption experiment using the non-size metal composite particles or the multi-metal complexes. So now I'm going to show in some details of these experiments. Okay, move on to the recent hit hot topics and with the non-composite particle. Okay, so hydrogen deuterium charging experiment with non-composite particles. Well, this was originally collaboration work with the institute, university and companies, and also this was supported by New Energy and Industrial Technology Development Organization in Japan. This is so-called NEEDLE project. And in this experiment, the following samples were examined. First, palladium, nickel, zirconia, PNZ, and copper, nickel, zirconia, CNZ sample. These are prepared by melt spinning method. And then second one is the copper, nickel, silica, CNS sample. This was prepared from the chemical synthesis, and non-composite absorbed on the pore surface of mesopolar silica. Okay, so for PNZ and the CNZ and CN samples, different mixing ratio of the composition was also examined. And the third one is the palladium silica. This is embedded palladium nanoparticles to the silica microparticles. This is called the PS sample. So this is an experimental setup, and this is a cell in which sample was put. And here are some experimental details, and charging the deuterium or hydrogen to this cell, and the temperature of the cell or temperature of the sample were measured by the LTD or thermocouples, and the loading ratio was measured by the changing of the pressure. And then from the temperature measurement, the excess power was estimated considering the reference lab result, calibration results. So then this is the result. This is a temperature behavior in a series of the experiment. This is, and so introduce the gas into the reaction chamber at room temperature. It's this part, and after a few hours, absorption is saturated and the associated heat evaporation terminated. Then the reaction chamber is heated, and it lasted for several days. Then at this point, the experiment is suspended, and the next experiment is performed. And this figure is the excess energy obtained from the left plot. And so from this plot, we found that the most sampled with binary metal non-composite produced excess power of the 3 to 24 watts, sustainably lasting for up to several weeks. And the excess power was observed in the palladium nickel with the deuterium and the palladium nickel hydrogen and the copper nickel hydrogen systems. And also the difference of the deuterium and hydrogen was also observed. And no excess heat was observed for the single element particle, that means the embedded palladium nanoparticle to silica microparticle or PS sample. And the excess power seems to depend on the ratio of the palladium nickel. So the larger excess was observed for the palladium to nickel ratio 1 to 10 rather than 1 to 7. And well, so this experiment was conducted by Kobe University group. And the same experiments were performed independently at Tohoku University with the apparatus they originally assembled. This is the apparatus they assembled, very similar to the Kobe ones. And they obtained a similar result with high reproducibility. In addition, the burst-like increase of the temperature at the gas inlet was observed simultaneously with the pressure increase there. So here, this is a plot of gas temperature measured by the thermocouple and placed in the gas pipe here, and the pressure of the reaction chamber here. So you can see the temperature and the pressure burst happen simultaneously. And also they found after the experiment, zirconia used for the filler, zirconia beads used for the filler in the cell was found to be broken. This is the same image of that same image, and the zirconia beads were broken. So that is indicating that the strong stress was given locally due to the heat burst. And this is a summary table of the results, and each line where experiment performs, sample type and gas type, and the temperature given, and maximum power obtained, and then the energy released per atom. So now the excess heat was observed with these samples, both in the hydrogen and deuterium. And from 2018, that is after the NEEDLE project completion, further studies have been performed in each group to improve the efficiency and to achieve the higher energy generation. And the Kobe University and Teknova Group has further developed the experiment. They have tried to optimize the sample conditions and treatment, and they found that 1 to 7 to 1 to 10 for the copper nickel or palladium nickel in zirconia supporter is good, and the sample can be reduced by repeated calcination, and the excess power increased by using the sample recalcinated after use. And this is some details of sample preparation, sample fabrication process. The nano-sized islands are supposed to be formed in this calcination process. So actually, they observed 2 to 10 nanometer diameter particles or nano islands or several microns support flakes. And they recalcinated the sample, recalcinated the used sample and tested, and then found the excess was much improved, like these table, the results. And the left table showed the copper nickel zirconia with the hydrogen experiment, and the left right one is the palladium nickel zirconia with the deuterium experiment. And the excess power were improved. You may find that excess power have been improved after recalcination. Okay. They have also found the interesting phenomena. This is a temperature behavior for the hydrogen experiment with the copper nickel sample. For the temperature of the upper part of the cell, LTD measured by the LTD4, plotted here. So you may find the anomalous heat burst with the under 30 watts peak power was observed, and this was only observed at the beginning of the temperature elevation phase here, yes, just here. And oscillatory variation of temperature was observed at gas outlet input. This is measured by the TC4 thermocouple 4. And this may be a same phenomena as reported by Tohoku University group I mentioned in the previous slides. So they have recently modified the experimental setup. The reaction cell was pressed horizontally and the gas supplied from the side to improve the uniformity of the gas diffusion to the sample. In this new experiment, they observed some unique phenomena. A two-step absorption behavior was observed. These are the behavior of the temperature and pressure inside the chamber and loading ratio, here black parts, and excess power, this purple parts. At the beginning, gas loading occurred rapidly here. And after it reached 0.9, the increase of the loading ratio slowed down. And so now we found there are clearly two phases. Okay, so the other characteristics is the correlation of the correlation between the loading ratio and excess power. There is a large excess power at the initial stage. It decreases the loading ratio saturated here, decrease here, and but it continues for more than 100 hours. I believe that these behaviors provide important hints for understanding what is happening in the process from hydrogen diffusion to the occurrence of the phenomenon. Another interesting and important result is here. This is the temperature of each part and the pressure inside the cell and the pressure of the gas reservoir here. Okay, so in the experiment, after filling the gas into the reaction cell, the valve LCV here is closed. The pressure inside decreases slowly due to the hydrogen absorption by the sample. And then after a certain period of time, this valve open, then the pressure inside the cell increase in bursts. That is dissolving the hydrogen rapidly. And the temperature RC, temperature of the reaction chamber, boosts up simultaneously. So this is an important result in establishing the method of triggering the reaction, along with the understanding of the reaction mechanism. Okay, so the following is the summary of what has been found so far in this study: the hydrogen and deuterium charging experiment with non-composite particles. And for synthesis type powder with hydrogen gas, about 200 to the 300 watt per kilogram per for a week has been achieved with 100 reproducibility under certain conditions. And the estimated COP, and it was found to be 1.2 to 1.4. And typical excess power is 10 to 100 megajoule per molar hydrogen, corresponding to the 10 to 100 keV per hydrogen atoms. So this suggests the nuclear reaction region, but of course we should still consider the non-nuclear explanation. And the two phases in hydrogen absorption, fast and slow absorption phase, and correlated excess heat generation were observed. And excess power can be reactivated by the resupply of the hydrogen by opening and closing valves after saturation of edge loading. So now moving to another topic, study with the multi-layer sample. Excess heat experiment using a nano-sized multi-layer composite. Well, this has been done by the Tokyo University and the Green Planet Group. The concept of the study is based on the considerable conditions for related researches. First of all, it's a NEEDLE project I already showed. And second one, the deuterium formation experiment using the palladium material thin film. This has been done by the Mitsubishi Heavy Industries Group and the Tokyo University Group. And in that experiment, the nuclear transmutation has been found. And third one is the deuterium absorption to nanostructure palladium nickel surface. This was originally done by Mizuno, and he observed the excess heat in his experiment, and then the Tokyo University and Clean Planet Group has successfully reproduced So then, from these studies, non-sized particle material or metal composite and hydrogen deuterium diffusions are the key for the reaction. So from these studies, considering these conditions, now the Tokyo University Group has designed a new experiment, excess energy measurement with nano-sized material, metal composite, and hydrogen gas. So this is the details of the experiment, sample preparation, sample types, and the copper nickel were deposited onto the nickel foil alternately by sputtering. In some cases, calcium oxide or yttrium oxide were inserted. And the material composite samples were mounted both sides of the ceramic heater via silica press. This is I mentioned this later, next slide. So this is these are representative samples they tested. So this is 3 sets of the copper nickel, and for example, this is 6 sets of calcium oxide, copper nickel combination. Okay, so this is a schematic view of their sample and reaction experimental setup. And here, this is a ceramic heater, and the material formed on the both side of the heater like this, here and here. And the sample is placed in the experimental chamber like this. And then this is some details of experimental procedure. And after baking the sample, introducing the hydrogen gas, and then the evacuating chamber, then heating up the sample up to the several hundred degrees Celsius. And then the measuring the sample temperature with the thermocouple and the residual thermometer. Thermocouple is embedded the ceramic heater here, and the thermocouple was placed outside the chamber. Then after that, cooling down the sample. And this procedure repeated several times. And also the blank run with the nickel bulk sample was performed to obtain a relation between the input power and the thermocouple temperature. And well, actually the details of the excess heat calculation can be found in this difference. I don't explain this much. I don't explain how they calculate the excess heat here. So you may find the details, this difference. Okay. So this is the result of excess heat measurement for each sample. And this is the result for 3 sets of copper nickel layers. And the blue plots show the pressure inside the chamber. So introduce the hydrogen gas, it's absorbed, so the pressure decreased. Then apply the power to the ceramic heater. After a certain period of time, turn off the heater, turn off the heater power, then introduce the gas again, and repeated that process. And this is the power applied the heater, and this is the temperature reached at that time. And red plots show the excess power obtained from the temperature measurement. So other plots show the for each sample type there. So now they found several interesting things. So excess heat tends to increase as the temperature increased. So for example, in this case, the input power is 90 watts. So excess power is here. So in this, the input power is 26 watts, then excess is larger than here. So excess heat tends to increase as the temperature increases, and the excess power varies depends on the sample type. Even with the sample, input power was upright. So even with the same input power, the excess power is different for each sample. And time dependence of the excess power is also different for sample type. And for the sample 3 set of carbon-nickel layers, and excess power decrease gradually here, but for the sample of 6 sets of carbon-nickel layers, the excess is gradually increased. So this increased behavior was only found in the 6 sets of layers. And there is a correlation between the amount of heat generated and the amount of hydrogen absorbed. So these are results they obtained. So here is a summary table of excess energy for each sample type, and this line the excess energy per hydrogen atoms. So the excess energy for 6 sets of carbon-nickel layer was the largest here. Okay, so the released energy per hydrogen atoms was on the order of keV or more, or keV or 10 keV. So this phenomena cannot be explained by a chemical reaction. And they have also reported some interesting result recently. This is a plot of the temperature measured on input power. Where you may find a kind of the heat burst here when the input power slightly changed. And in this case, the input power changed to 25.8 watts down to the 25.0 watts and back to the 25.8 watts. But this light plot, this did not happen in different conditions. In this case, changing input power 26.3 watts to the 25.8 watts, then back to the 26.3 watts. But so in this case, the heat burst didn't happen. So now we would say that there is a condition to be considered for inducing the heat burst, such as the composition and the state of the sample, the surface temperature of the sample, and the amount of the time range of the input power perturbation. So if these well optimized heat generation could be controlled, maybe we would say the heat generation could be controlled by optimizing these conditions. So another interesting result, infrared emission correlated with temperature behavior was observed. This is the time variation of thermocouple temperature and the intensity of infrared emitted. So they observed the behavior of the temperature measured by the thermocouple. Thermocouple is embedded by the heater here, and the intensity of the mid-IR, which corresponds to the, which is the 0.23 to 0.41 electron volts. These are synchronized. So that is indicating energy generation near the surface of the sample. Also, they found another infrared visible light correlated with synchronized with the thermocouple temperature. Yeah. The infrared with the energy 0.8 electron volt and 0.92 electron volt. Also, they observed visible light. So this is very interesting result. So this is a summary of what has been found so far in this study. The excess power of the 1 gigajoule mole H, and about 10 keV per hydrogen atom has been observed. And this excess heat generation was observed almost 100 reproducibility. And ratio of output power to the total input power, well, so-called COP, is 1 to 2 in the case. And released energy in order the keV, 10 keV per mole per hydrogen atom. This is difficult to be explained by a chemical reaction. And effective method of inducing the reaction are being elucidated. And it has been observed that infrared radiation is emitted over a wide range of wavelengths in synchronization with the temperature change. Okay, let me summarize. In recent years, many important results have been obtained in the hot gas experiment using the nano-sized metal composite particles and using the multi-layered metal complex. Excess heat has been observed with good reproducibility, and it has been observed in both hydrogen and deuterium experiments, and observed the excess power that implied that it is possible to be nuclear reaction origin. And the study for the improving the efficiency and increasing generated are going by to optimize the conditions for sample treatment and the experimental procedure. And for further studies, experiments in which conditions were systematically varied to clarify the trigger condition and to clarify the reaction mechanism. So engineering studies for the demonstration of the practical use of the reaction. This was needed for the further studies. And it is also important to study the transmutation. That is another interesting topic in gas phase experiments. This should be done in parallel with the excess heat study. Okay, finally, I'd like to thank Professor Takahashi and Professor Yamura for providing materials and feedback to this presentation. Okay, that's all for. Thank you.